Hello, Professor Sardi here with you again. We're going to take a look at a question that would seem to be from calculus, but that could be deceptive. All right, so here's our question, and I'm going to follow this up with a diagram. Because we are dealing with these poles being perpendicular to flat ground, then we have right angles here and here. A and B will both have to be greater than 0, because if they're not, then we don't have any poles. In the diagram, I have A greater than B. We don't know if that's necessary, though. You could have A equal to B. You could have A less than B. We don't know yet. C, the distance between the bases of the two poles. That will have to be greater than 0. Because if it's not, then you have no space between the two poles. The two poles are the same, and there's no place for them to meet. The distance from the base of the height with pole A to where the wires meet is x, and so what's left over, c minus x, is the distance from its base to the meeting points. Because we are dealing with right angles and therefore right triangles on the left and on the right, I've applied the Pythagorean theorem. The square root of a squared plus x squared, that is the length of the hypotenuse of the triangle on the left. It is also the portion of the wire that goes from the top of the pole with height A to the meeting point on the ground. And so similarly, this is the length of this portion. And we want to minimize the total length of the wire used. This function is dependent on x. What that total length will be continuous. Notice that a squared plus x squared and b squared plus c minus x, that quantity squared. These will be greater than 0 because although x could be 0, we could have the wire going directly from the bottom of the pole with height A to the top of the pole with height B, or vice versa. We could have this so that x could be between 0 and c inclusive. X squared and c minus x quantity squared, those are going to be non-negative, added to strictly positive values, a squared and b squared. So what's underneath both those square roots will be strictly positive, and this function will be continuous. This function will be continuous on the closed interval from 0 to c. We could apply the properties of limits where we first split the limit across the sum. Then, since the square root is dealing with strictly positives underneath, then we can bring the limits inside. Then, again, split up the sums inside. The limit of a constant is a constant, as we see here. The limit of a power is the power of a limit. And then that final part on the second square root, we would have brought in inside of the squaring the limit of c minus x. Again, split the limit across c minus x, and the limit of a constant is a constant. Without showing all of the details, the limits would exist. And not only that, as I mentioned, along that closed interval from 0 to c, the function would be defined everywhere within that. The limit would exist everywhere within that. And the limit as x approaches some value within 0 to c would equal the value of the function that x is approaching. Now, because I'm talking about the function being continuous on 0 to c, what I'm hoping to apply is the extreme value theorem. In this case, rather than talking about the closed interval AB, I'm talking about the closed interval 0 to c, and there must be an absolute maximum value and an absolute minimum value over that interval for our continuous function, in this case, t of x. So I need to find the derivative of t and the critical points of t, make sure that they're within that interval, test the value of the original function, and test the value of the original function at the endpoints, and at the critical points. Now, to take the derivative of t, I'm going to need to apply the chain rule. And to do that, I have rewritten the square roots. Take the quantity that was inside each square root and raise it to the 1/2 power. Apply the chain rule from there. So here we go. Power rule, bring out the 1/2 in front. I still have what was inside, now raised to a power that is 1 less than the original exponent. And I'm multiplying by the derivative of what's inside. So take the derivative of these two terms, but a squared is constant, and the derivative of a constant is 0. The derivative of x squared is 2x, and multiply by that. Then, similarly, except for one more wrinkle, for the second term. When I take the derivative of what's inside here, again, b squared, that is a constant, but taking the derivative of this term, I have to apply the chain rule again. So we've got 2 times c minus x times the derivative of what was inside. C being a constant, derivative of negative x is -1. Before trying to find the critical point, doing a little simplification, the 2's cancel, both here and over here. Bring the x in front, just a little easier to look at. Similarly, bring the negative, plus a negative would be the same as minus. Bring that to the front, and the c minus x to the front. And there is a simplified version of our derivative. So now I need to find out, where does that equal 0? Let's add this portion to both sides. Let's square both sides, and as part of that, for lack of a better word, distribute the squaring to the 2 factors here and the 2 factors here. Squaring of this factor will get rid of that denominator in the exponents. Let's multiply both sides by the first power of this and of this. So that, for example, we'll see this part canceled on the left side, but show up to the first power on the right side. Similarly with this portion. Let's expand this as we work to solve for x. First, taking care of the quantity c minus x, all of that squared, showing up in 2 spots. And on the right side, distributing the x squared, seeing the x cubed and the x to the fourth is making this look really not so nice, along with the fact that we also have the a, b, and c in there, but x is what's being treated as the variable. On this side, I'm distributing the a squared, and then I'll add to that distributing the x squared. And that really doesn't look very nice, but notice that these last three terms show up exactly the same on both sides. We can cancel those out and subtract b squared x squared to the other side so that everything will equal 0, and the highest power of x that we'll have is 2, so that we're dealing with a quadratic in terms of x. Writing this in descending powers of x. And furthermore, I will factor the x squared out. So solving that for x will hopefully we'll be able to find out the critical value or values. And I'm going to apply the quadratic formula. Doesn't that look like something that would be fun to simplify? But we have to do it. Here I've taken care of the two negatives canceling each other out. I've squared here. Here I've just brought the a squared c squared to the front so far. We have as a common factor 4a squared c squared. So I'm going to factor that out. And I need some more room again to continue simplifying. All right. Distributing that subtraction. And then combining like terms here. That's starting to look nicer. Let's see here. Taking the square root of each of these factors. To a, I'm going to put the square root of the b squared first. So the square root of 4a squared, c squared, b squared would be 2acb, but I've written that as 2abc. And I'm going to factor out 2ac in the numerator, leaving us with a plus or minus b. All over 2 times a minus b. Got a little error there. I'm going to factor in the denominator. By the difference of squares. Now, I haven't mentioned it yet, but the a squared minus b squared cannot equal 0. Of course, the 2 is not 0, so we're not worried about dividing by 0 there. But a plus b was equal to 0. Then a would equal negative b. But b was, should have said here, strictly positive. Sorry about that. Then that would make a strictly negative, which would contradict that a was strictly positive. Okay, so that can't happen. A minus b cannot equal 0. So we cannot have a equal to b and get this solution. Talk about that more in a bit. Then in the first case where we have the subtraction, we can cancel the 2's and the a minus b's. In the second case where we have addition, again, cancel out the 2's, this time cancel out the a plus b's. The second one is a problem, because if we rewrite that fraction, since b is positive, a minus b will be smaller than a. Dividing something by something smaller than itself will give us something greater than 1. That would give us that x would be strictly greater than c, putting it outside of that interval. That is not possible. So we reject this. It's not a critical value within our closed interval. We're dealing with that as the only critical value within our closed interval. So by the extreme value theorem, we needed to test value of that original function at the endpoints and at the critical value that is strictly in between. And it's not so difficult to see what we would have from the endpoints. It's going to take a fair amount of work, though, plugging this in. Putting in 0 for x. 0 squared is 0. A squared plus 0 would be a. Square root of a squared, since a is strictly positive, is a. Putting in 0 for x over here. C minus 0 is c. So we'd have the square root of b squared plus c squared. It's going to be very similar when we put c in at the other endpoints. First square root would give us a squared plus c squared. Adding to that what we get from the other square roots. Well, c minus c is 0. 0 squared is 0. B squared plus 0 is b squared. Since b is strictly positive, the square root of b squared would be b. Let's use some space down here to plug in the value of x that we found for the critical point. This is finding out value of t at that point. Whereas this was t of 0, and this was t of c. All right. So first of all, I'm going to get a common denominator here. A plus b multiplied to top and bottom. Distribute the c to the a plus b. And when we put together these two fractions with the same denominator, then subtracting those numerators, we're going to get the ACs to cancel. So that under that second square root, after the b squared, all that's left of the second term being squared there, under the second square root, is BC over A plus B. In each case, on that second term, under each square root, I'm going to split up the squaring across the quotient and across the product in the numerator, taking two steps in at the same time. And seeing that, within the first square root, I'm going to factor the a squared out of both of those terms. And on the second, similarly, b squared. That's starting to look a bit nicer. Let's get a common denominator again. And then add. Same for both of these square roots. That's all right. Now that may not look as nice as it did a moment ago because I've got the common denominator. However, things are really going to shake out pretty quickly here. Split up the square root across the quotient and then across the product that's in the numerator, taking those two steps at the same time. Do the same for the second square roots. Because A and B are strictly positive, A plus B will also be strictly positive. So take the square root here, here, and in the denominator, here's what we see. There's from the first square root. There's from the second one. And I'm going to factor out the square root in the numerator here and here are the same, and we've got the same denominator. I'm going to factor out those, and we'd be left with a plus b from here times this. Remember, we'd already mentioned that a plus b could not equal 0. These are going to cancel out. And we are just left with the value of the original function t at the critical value of x is this. All right. Now we need to find out which one's the smallest. I'm just going to show that at the critical value that it is smaller than this one. In other words, that this is greater than this, because we have very similar looking expressions at the two endpoints, looking just like an interchange of B and C. So I want to show is a plus the square root of b squared plus c squared greater than the square root of the quantity a plus b squared plus c squared. All of that under the second root. Without going into all the details again, I've shown this in a previous video, which will be in the same playlist as this one, that if you square both sides, it's going to keep things going in the same direction, at least with the types of numbers we're dealing with here. And then whatever I write here, when you backtrack, although it's for a related but not quite the same reason, the same thing will hold. That the inequality will be going in the same direction. So squaring both sides. Just going to cancel out the square root over here. And that will give us a squared plus 2ab plus b squared plus c squared on the right-hand side. On the left-hand side, expanding that. We'll get cancellation here. Cancel out the a squared, b squared, and c squared that we have from both sides. So that now we're trying to check whether 2a square root b squared plus c squared is that greater than 2ab. Since a is greater than 0, and of course 2 is greater than 0, we can divide both sides by 2a. So this boils down to is the square root of all of b squared plus c squared greater than b. Well, since c was strictly positive, then c squared is strictly positive, and adding that to b squared will give us something greater than b squared. Taking the square root of something smaller will give you a smaller square root. And since b was strictly positive again, square root of b squared is b. So, since we have a true statement there, it can be reversed. The reasons can be given. I've given them elsewhere in a different video in this series. And so we do have that this is less than this without loss of generality. It'll also be less than the value of t at the other endpoints. So this, in fact, does minimize t, this value of x, minimizes t of x on the closed interval 0 to c. What about if a had been equal to b, though? If a is equal to b, if the two poles are of the same height, then the function t becomes that, with this as the derivative, and again, we will cancel out the 2's, etc., etc. Set that equal to 0. Add this portion to both sides. Square both sides. Multiply both sides by something so that we don't see negative powers. Without expanding the c minus x quantity squared parts, let's just distribute it over here. And here, let's distribute the x squared. Then we see that we can cancel the common x squared times the quantity c minus x, all of that squared. Furthermore, since a is strictly positive, then so is a squared. Divide both sides by a squared. Take the square root of both sides. X is equal to plus or minus c minus x. Now, by the way, remember that x is not negative. And since c is greater than or equal to x, c minus x will be non-negative. So that when I take these square roots, then we don't have to worry about imaginary numbers. Okay, so this means that either x is equal to c minus x, or x is equal to negative c minus x, giving us either 2x equals c or 2x equals negative c. C was strictly positive, which would make 2x equal to something that is strictly negative in the second case. And that is not possible because 2 being positive and x being non-negative, then this would have to be non-negative. That cannot equal a strictly negative. So we reject this. And we just have that 2x equals c, so that x equals c over 2. Let me write that up here. So that would be halfway in between the two bases. We put in 0 to the first. 0 squared 0, a squared plus 0 is 0. We've got the square root of a, but a is strictly positive, so square root of a squared is a. Put in 0 here, c minus 0 c, c squared then. We have the square root of a squared plus c squared. And at the other endpoint, we put in c for x. C minus c is 0. 0 squared is 0. A squared plus 0 is a squared. Take the square root of that non-negative a squared, and we just have a. Okay, so we're looking at the same thing at either endpoint when a equals b. What about when we put in c over 2? Or x. C minus c over 2, that would be 2c minus c all over 2, so just c over 2. In other words, we've got the same thing under both square roots, so 2 times that. So comparing what we have at the critical value to the endpoint, same thing at either endpoint actually. So again, let's square both sides. Over here, splitting up the squaring to the 2 and then the square root factor. Let's combine the like terms here. And where the c over 2. Distribute the 4. Cancel our c squareds. Subtract 2a squared from both sides. Subtract 2a squared. 2 is positive, a is positive. Dividing both sides by 2a. All right, so c strictly positive, c squared strictly positive, added to a squared. That's something bigger than a squared. And when you take the square root of something larger, you get something larger. Also take note that if we had put in b here as equal to a, combine those like terms in the denominator, remembering that a is strictly positive, so canceling out, we get that c over 2. So really, even if a does equal b, then we can say that for this value of x, that it will minimize the function t. This is giving us an expression in terms of the heights of the poles and the distance along the flat ground between the 2 poles that will minimize the total length of the wires. But hold on, we're not done yet. So hold on. We thought about geometry when we applied the Pythagorean theorem. And we're finding that when we plug in the critical value that's within the closed interval, that's looking like a result from the Pythagorean theorem as well. The a plus b that we're squaring in there, then adding c squared, taking the square root of that a plus b. Why are we talking about the sum of the heights of the 2 poles? Okay, well, I'm going to flip over some vertical axis, the triangle that was on the right. Take a look at what we've got here. You can do a little bit more besides the vertical flip. Having done a vertical flip to the triangle on the right, now I've also moved it down. Can you begin to see where the a plus b is coming in? If we extend the vertical line segment from the pole of height a further down, and similarly extend the base of the triangle that had a height of b, they're going to meet up at a right angle, and we have a total over here on the left of a plus b. for the length of this overall line segment. Take the solid part plus the dashed part. And along the base here, we've got x plus c minus x. Sorry, the c minus x is no longer showing up. But anyway, the total then would be c. Therefore, the value of t at the critical value, where we had the quantity a plus b squared plus c squared, the square root of all of that, would be the length of the hypotenuse of this overall large triangle, where we had a height of a plus b, a base of c. And again, this part right here, that is the length of the hypotenuse. What else? What we have here, that would be the square root of a squared plus x squared, whatever the value of x is within that closed interval 0 to c. And what we have here, this would be the hypotenuse of this right triangle that had a length of, take b squared plus the quantity c minus x got squared, add those two together, take the square root of that, and you get the length of that hypotenuse for whatever the value of x is within the closed interval from 0 to c. Well, the triangle inequality tells us that if a and b are different, then the length of that third side would be less than the sum of the other two. Regardless of whatever the value of x is, as long as it's within that closed interval from 0 to c. Now, if a and b are equal, then these are going to line up nicely. We won't get a third triangle here. I haven't shown it here. Really, it comes up elsewhere in another one of my videos. You could talk about the slope. If a and b are equal, that this line segment would continue on here, giving you the value of the critical point, and then the total length would be 2 times the square root of a squared plus c over 2 squared, if I remember correctly. But in any case, busted. This was not a calculus problem, really. It was a geometry problem. And again, this is whether a and b are equal or not. Hope you watched that all the way through to see how we can be misled by the sound of a problem, what we really need to apply.